Welcome to homework set number 1 for ECE 463-663. This homework is kind of a review of signals and systems. The first problem is going backwards. In signals and systems, you look at, given a transfer function, g of s, and an input, find the output. Well, this is, if I know the input is a step input, I know the output, find g of s. This is the idea of a dominant pole. G of s could have a bunch of poles. One of them really dominates the response. If that pole is real, I could approximate this as a first-order system, a over s plus b. So I need to pull two pieces of information off this graph. One of them that's pretty easy is the DC gain. Plug in s equals 0, I get a over b. At DC, I'm right here, about 1.45. A second thing that's easy is the transient decays as e to the minus bt. When that's 0.02, or 2% of the initial value, I misspelled 0.02, 0.02, take the log of both sides, they get minus bt is minus 4. That's why we like the 2% settling time. The log of 0.02 is minus 4. It's actually minus 3.97, pretty close. That says that the settling time is 4 over b, or b is 4 over the 2% settling time. So in this graph, here's the 100%. Figure out where it's roughly 2%. It's kind of hard to read off the graph. Somewhere in here. That's my settling time. That lets me find b. Once I know b, I know the DC gain, I can find a over b. So if the DC gain is 1.45, that's a over b. If the settling time is 1.3 seconds, then b is 4 over 1.3, 3.08. I know the DC gain is 4.05, so solve for a so that the DC gain is 1.45, gives you 4.46. Here's roughly the transfer function. So that'd be your first order approximation for this system. This is actually second order. I can tell because instead of going up right away, it's kind of flat right here. So this is second or third order. The fast poles are really hard to see. Pretty much all you see is the dominant pole, hence the name dominant pole. Problem 2. If you have oscillations, I know right away this has complex poles because I've got the complex pole that gives you the oscillations and its complex conjugate. So the transfer function will be in this form or factored out in this form. The DC gain will need three pieces of information off the graph. One is the DC gain, right about here where it settles out. Another one would be the frequency of oscillation. And the third one would be the settling time. So if I say the DC gain is roughly 1.15, that would be, this is s goes to 0. If I've got 1 cycle, 2 cycles, 3 cycles in about 1.64 seconds, I can tell you omega d. So that's 3 cycles in 1.64 seconds times 2 pi, because Hertz is English. Anything English is not natural. 11.49 radians per second. And the settling time, where there's got an envelope in it. Where's the envelope squeezed down to about 2%? I don't know, 2 seconds-ish. Hard to read exactly. About 2 seconds. Tells you that 4 over sigma is 2. Solve for sigma. The real part of the pole is 2. So my poles are at minus 2 plus J11. This tells you the settling time, tells you the frequency of oscillation. A is just a fudge factor, whatever it takes to make the DC gain 1.15. So it's roughly G of S in factored form, G of S multiplied out. And again, your numbers will be a little bit different. It's hard to read the graph to 5 decimal places, but something close to that. Problem 3. If I have a transfer function, what's it mean? This really means I've got a third-order differential equation. If I cross-multiply, multiply it out, s means derivative, so my differential equation would be the third derivative of y, plus 24 times the second derivative, plus 171 times the first derivative, plus 324 times y, is 50 times the derivative of x, plus 350x. This is the differential equation that corresponds to that transfer function. And you can kind of see it by inspection. the denominator polynomial is times y. The numerator polynomial is times x. Where transfer functions are useful is they let you solve for various inputs. If my input is a sine wave, this is for all time, that's a phasor problem. The frequency would be 7 radians per second, S is J7. The input in phasor form is 2 minus J5, real parts cosine, minus J is sine. This is the gain everywhere. All I care about is what's the gain at 7 radians per second, times the input at 7 radians per second. That gives you a complex number. What it means is the real part's cosine minus J is sine. There's my answer. If my input is 0 for time less than 0, and then kicks on at t equals 0, that's the Laplace transform problem. In this case, I take the Laplace transform of x, which is just 1 over s. Here's my transfer function. Multiply the two together, I get y. So there's y in terms of s. To find y in terms of t, I need to take the inverse Laplace transform. And one approach is to use partial fractions. Ignore this term, plug in s equals 0, and evaluate to get 1.08. If I ignore this term, cover it up, plug in s equals minus 3, I get this term. Likewise for minus 9, minus 12. These I can write, take the inverse Laplace transform. That's 1.08 minus 1.2 e to the minus 3t minus 0.6 e to the minus 9t plus 0.77 e to the minus 12t. If I want a first order approximation for the system, what I do is I keep the dominant pole, that's the pole closest to s equals 0, and match the DC gain. So here's my dominant pole, keep that, find the DC gain. The DC gain of the system is 1.8. Pick the numerator to make the DC gain 1.08, gives you 3.24. That's roughly g of s. To check, I could plot the step response of the third order system, call that g3. Step response to the first order system, call that g1. Input the two systems. Let's go from 0 to 2 seconds. Find the step response of g1. Find the step response of g3. Plot the two together. And here's what you get. Here's the first order system. There's the third order system. Same shape, same DC gain, same settling time. It's roughly the same system. There's a little bit of extra delay. So sometimes you'll model the system with delay. Oftentimes don't, because delays don't model in state space very well. So oftentimes we don't do the delay just because it doesn't fit our solution. But a better model would be first order system plus a delay. So that is homework set number 1 for ECE 463.